This accident occurred in 1959. I was between my freshman and sophomore year at Vanderbilt University. After I graduated, I had a health physics fellowship from the Atomic Energy Commission and studied health physics and was the campus radiation safety officer. I spent a summer at Oak Ridge working in a pilot reprocessing plant as a trainee in health physics. I went on to study physics, high energy physics, spent a couple of years in the Navy, eventually ended up at the Natural Resources Defense Council. So that's sort of by way of my background. I was asked to look at this accident a few weeks ago and was supplied with about 80 documents and got some additional documents. I don't pretend to have read everything, and I don't think any of the speakers here have read everything. I would like to make several sort of general observations. First, this was not the only reactor accident at the site and not the only source of off-site exposure to toxic materials, both nuclear and non-nuclear, from the site. Secondly, this accident occurred at a different time. By today's standards, you would say well, first of all, I would say the safety of a nuclear plant depends foremost on the safety culture at the plant and not on the design of the plant. And in today's environment, had this accident occurred today, you would say the safety culture was appalling by today's standards. But this was a different time. But I also think it was not appropriate even by the standards of 1959 or the early 60s. And I've provided you with a written statement, which it will be more detailed than I can cover in 30 minutes or so here. And I've given you on page 2, a quote from a book written in 1964 by MIT reactor expert who went to MIT to design the research reactor, the MIT research reactor. Later became, or was then on the advisory committee on reactor safeguards, the AEC, and later became a commissioner, an atomic energy commissioner, Tommy Thompson. And in this book he wrote edited, and he wrote this particular chapter in '64. He too believes that the activities related to operation of this particular reactor were inappropriate for the day. Another observation is that there's been a lot of debate about this accident in recent years. Much of it generated by some early work by Dan Hirsch and his students. Dan is here today. But there was a class action lawsuit. An attorney on behalf of a class filed a suit against Boeing, called O'Connor versus Boeing, that was settled. I don't know the details of that suit. I believe it was settled for something on the order of $30 million. Part of the settlement agreement was that the expert testimony would be sealed. This was a demand by Boeing, so that the testimony of plaintiff expert witness Arjun Makajani, Dr. Makajani, would not be made public. So that testimony has not been made available to any of us speaking today. Although the testimony of the defendant experts in rebuttal has been made available by Boeing. So Boeing insisted on sealing Makajani's testimony and then has released its own expert testimony. I don't know whether that's in violation of a court order or not. But it makes the analysis somewhat unfair, skewed, to have one side of the argument available to those of us reviewing the accident and the other side of the argument not available. But that's the way it is, so, and we're working off of what we have. Now, when all is said and done, this, the debate that has gone on about whether there was significant releases off-site or not boils down to, I'd say, two scenarios. One scenario you heard by the previous speaker, Dr. Picard, and you'll hear that again, and that is most of the item was never left the fuel. The other scenario is that there was significant melting of the fuel and voiding of the channels between the fuel elements, and noble gases and sodium and bubbled up to the surface of the cover gas, was from there pumped to the decay tanks, and from there released through the stack. And so the debate is all about, where do you come out? Did it stay in the fuel, or did it go through this other leak path? Now there's another leak path, and that's through the penetrations in the reactor head where you load fuel, and into the reactor building and out the exhaust system for the high bay area of the reactor building. When I look at that leak path, I say that the evidence doesn't support that being a primary, and there was clearly leaks and radioactivity through that pathway, but the amounts probably appear smaller than what would be needed to cause any significant harm off-site. And so I think there are really these sort of two alternatives. And I've had the benefit of discussions with Sandia in preparing this for this presentation, and also benefits of discussions with Professor Denning, who will follow me. Lacking sort of detailed measurements off-site at the time of the accident, what we've all tried to do is reconstruct what was in the reactor, what was available to be released, and what the pathways were, and make those assessments. I think the, if I could go to the, okay, which one? All right, you've seen this slide presented by Sandia, and I'm relying on Sandia for these data. I don't think there's any dispute about the calculations of what was in the reactor at the time of the accident in terms of the fission product inventories within the uncertainties of these calculations. So these data, I think, are quite acceptable. You have heard some discussion previously about, and these figures are all in the handout, so I'm now looking at a table on page 10. Now we're just looking at the noble gases and volatile fission products, krypton, xenon, noble gases, and iodine, cesium, and strontium. And there's an effort to sort of put a range on how much of the fission products are in play, because a lot of the fission products are in fuel slugs that were not damaged. And we would all agree that those are not in play. Those would not have gotten out in significant amounts relative to what the damaged fuel. So it's unfortunate. There's some terrific pictures in some of these early documents of damaged fuel. The Xerox copies turned into PowerPoint presentations don't do justice to the pictures. If you can ever get your hands on some of these original documents and roll out the pictures, you will see that this fuel, it's a mess. I mean, it was damaged badly. Of the 13 assemblies, the fuel in the 13 assemblies was really damaged. It's something on the order of 20%, but there's a big, I mean, this is an eyeball guesstimate by Sandia, but let's accept that number. Now, those fuel assemblies are the damage occurs primarily in the center of the rods, not at the two ends, because the fuel burn-up and the production of fission products is not uniform across all of the fuel assemblies. It's highest in the center. And so there's a distribution radially, and there's a distribution axially. And so when you say 20% of the assemblies are damaged, you need to do some sort of correction for the fact that the damage occurred where the burnup was highest, and therefore where you get more of the fission product. So if you say 20% or 30%, that's 6% of the total fuel is damaged. And so I said, well, now this is just no real science here. I say, because of these other factors, it could have been, say, 10%. You can make arguments it's higher, but just for sort of bounding the problem, my upper limit is on the order of 10%, recognizing some people would go higher. And then you've heard arguments about material sticking in the fuel and evidence from noble gases that the number may be more down in the 1% range. So I've got in my table on 10, low, mid, and high, and for the noble gases, I don't have the low number. But that's the activity that I think is in play, not the 1.6 million curies of fission products and other activity in the entire reactor, but this amount. And so this sort of, at this stage of the analysis, bounds the problem. Now, after the accident, and beginning on August 2nd, there were measurements made of the activity in the cover gas and the activity in the sodium, and then they were back calculated to account for radioactive decay to the end of run 14 or July 26, what the activity would have been in the cover gas and sodium. And those are the Hart numbers presented on page 11 in my book and presented here in this slide. And if you look, you see down there cover gas, not much there. And a lot of the debate, earlier the debate, at least on one side of the debate, a lot has been made of the fact that there's only the krypton and xenon were found in the cover gas. In my view, these data of what was measured after the accident have no relevance to what might have been released during the accident, because the cover gas was pumped over the course of the run, pumped into the decay tanks and replenished with fresh helium, and done that on multiple occasions. So what ended up in the cover gas at the end is not particularly relevant to what got pumped over into the decay tanks and released. So you compare sort of, and by the way, there's a 1959 quarterly report written by Atomics International on what was vented. And you sum up the numbers, and it's on the order, in this one-pager type page, it's on the order of 28 curies of noble gases. And so you say, okay, if you go back to my earlier slide, there's some numbers of that are much higher in terms of what's at play compared to what has been said got out. What happened? How do you account for the difference? Now, first of all, I want to say, not first, but I want to say that the noble gases, even if they got out, wouldn't have, this is a small reactor. This is, in terms of its power, it's 128, it's 20 megawatt thermal, 128 times smaller than TMI-2. So the inventory of the noble gases that are at play is smaller than what could have caused any serious harm off-site. So we're not talking about, in terms of potential off-site releases, the issue is not with the noble gases, the issue is with the volatiles, with iodine, cesium, strontium, but we'll start with the iodine because that's the most volatile of those three. So what could have happened? I think that we're now down to three scenarios. It either stayed in the fuel, or it got into the cover gas and leaked through these penetrations into the high bay area and was vented. Or the third one, got into the cover gas, was pumped into the decay tanks and vented through the stack. So I think we all agree on the scenarios, and now we're going to debate the significance of those three alternatives. Now, here's the first problem, or one of the problems that we face. Here's some cover gas measurements, and this is I'm copying from early documents, an interim report, and it's shown in my presentation on page 7. Run 14 begins over here at day roughly 195. Day 196, if you can go on the web and go to what day of the year it is in 1959 on July 15th, and you plug in July 15th, 1959, tell you it's day 196. So there's 196. There were no radioactive activity measurements in these tanks in the gas decay tanks until July 15th. This is several days after the accident occurred, after the run started up, and after there's evidence that of high readings. And moreover, in the first reading, it went off scale. So if there was releases to the tank and tank to the stack, you don't have good data for what was in the tank, and you don't have any measurements of whether it's noble gases or what fraction of iodine and so forth. This is a picture or a graph also in my paper on page 8 of activity in the high bay area. Now, earlier I said, well, I don't think this is the critical path for off-site releases relative to the vent tanks, but I want you to notice that as soon as they started up the run on the 12th, they get these high readings. In fact, you'll notice that there are about 4 or 5 of these spikes where the monitor in the high bay area went off scale. All right? You got to ask why they kept running this reactor. It goes off scale. They know they think they got activity in the cover gas. So if you want to go into the high bay area and patch the leaks, one thing you're going to do, you know, if your bathtub's overflowing, the first thing you do is turn off the water. So you pump the gases in the cover gas into the decay tank so it quits leaking. So they're starting on day 1, they're starting to pump radioactivity into the tanks. That's my view. And in fact, when they get around to measuring the radioactivity in the tank on the 15th, several days later, it's off scale. Something's going on, and it's called fuel melting. Now, you saw an argument by Sandia based on some thermocouple measurements that fuel melting was probably on day 20, on the July 23rd, 24th, somewhere in there, because that's when high readings of the thermocouple were. There's also the thermocouple, there's evidence in the literature that you shouldn't rely on these thermocouples readings, and in any case, the thermocouples were not where the melting was. They were elsewhere in the core. But you're getting evidence early on of something really bad going on that's pumping radioactivity into the high bay area. And then you get evidence on the 15th that you're off scale in the cover gas. And then there's evidence in the interim reports, the early 1959 reports. You try to find out, well, when did they vent the tanks? There isn't a list, except there's this quarterly report that they prepared in November of 1959 on the venting. And I reproduced this on a spreadsheet. I did it so I could calculate the numbers. I couldn't find a way to copy from the actual report to the view graph. So here are the dates. And the first thing you notice, first thing I notice is they've got venting on the 20th, 25th, 29th, those occurred during the run 14, but there's no listing for the 15th. And they vented on the 15th. There's other evidence that they vented on the 15th. The high stack readings on the 15th. So there's nothing in here. There's no data in here for the venting during the period of interest from the 12th to the 15th. Some of these numbers is the 28 Curies. It's the Boeing number today. You heard it if you were on the tour yesterday. Phil said, you know, we think they released 28 Curies and it was all noble gases. And that's where that number comes from, I think. And of that, about 11 or 12 Curies are during the run, and 17 Curies or whatever it is are after the run, after they've shut the reactor down, they're cleaning up. So I don't accept this as a complete and accurate summary of what was released. And therefore, I don't accept Boeing's statement that only 28 Curies of noble gases were released as an accurate and acceptable statement of what was potentially released. Now, there's another sort of puzzling thing about this that, as far as I can tell, I mean, maybe my colleague to the speaking can correct me. Up here, there's a word particulate. If there were only noble gases released to the cover gas, there shouldn't be any particulate. But now my problem is I can't figure out how they got these, where these numbers come from. I understand what kind of radiation monitor they had. And by the way, also there's even one sort of peak that somebody erased because there's a suggestion or evidence that they thought at the time that it was an error in the pin, or in, you know, so they just, I don't know whether it was or not, but it got erased from the chart. But there's no measurements in the high bay area of particulate versus noble gases. But we know this was these air monitors had filter paper, and you suck air through the filter paper, and you try to deposit particulates on the filter paper. Filter paper moves over under a Geiger-Müller tube, a detector, and then you count what's on the filter paper. You can make corrections for geometry and efficiency of the counter, and then calculate how much particulates, how much radioactivity was in the air that got captured on the filter paper. If it were noble gases, they wouldn't be captured on the filter paper, and the air monitor would be reading whatever, just ambient noble gases. There's no way that I can see to unravel whether there were iodine leaking up from the cover gas into the high bay area. And similarly, there are no measurements, there are no spectroscopic measurements of the activity in the holding tanks. So you have one theory that's based on, the polite word would be phenomenological chemistry considerations based on more recent science that says this stuff should have been stuck in the fuel. You look at the pictures, you say there's no way that stuff is stuck in the fuel. But when you listen to the phenomenological chemical explanation, and I'm not a chemist, so I'm not going to take a position. I mean, I think it's a very logical argument, acceptable argument. Okay, if that's true, where's the analysis of the other two accidents that were just like this? EBR1 had a fuel meltdown accident. It was sodium cooled fast reactor, fuel meltdown. Fermi 1, channel blockage just like this, fuel melting. Nobody, either for lack of time or because there's no data or because there was no releases of iodine, has made an assessment of the two other accidents that should shed light on what the iodine release fraction is. So you have on the one hand this argument that it's in the fuel, and the other argument is in this early period before the 15th, you had voids in the channels, fission products, volatile fission products released into these voids. They bubble up through the extra meter of sodium on top of the core, and then there's a question: did the bubbles collapse and the stuff get absorbed in sodium and you don't see it, so it must have stayed in the fuel, or did it get to the cover gas? There's no data on it. Nobody's done the modeling to understand whether the voiding and whether the bubbles would have gotten to the top. The sodium's moving at a meter, 5 feet a second, so it would have moved up fairly quickly. The bubbles would have moved up fairly quickly. So the scenario is it gets to the cover gas. They're in trouble in the high bay area. They got leak-ins. They're trying to patch this stuff with tape. They send some guys in the high bay area and try to tape some of these what they think are the leaking holes, and so they dump the cover gas into the tanks. Now there's also another little problem. Between the tank and the stack, there's a filter. But if you go look at the engineering drawings, there are pipes and valves to allow you to bypass the filter. And they're, in fact, pipes to allow you to bypass the storage tanks. So you can dump the cover gas directly in the stack by flipping a switch in the control room. And there's statements in the record that when they can't quite figure out these high readings, well, maybe someone inadvertently left the switch in the wrong side. So there's a lot of uncertainty about whether this stuff could have gotten to the cover gas, and if so, how much got out. And so you have these two competing scenarios. My bottom line is there's not enough information to make a judgment as to what fraction stayed in the fuel and what fraction got out. I do believe that the noble gases eventually, the krypton 85, which wouldn't have had time to decay significantly, would have gotten out eventually, but there's not enough there to cause a lot of harm. When I look at the numbers, I don't think the maximally exposed individual, the individual risk to anyone that was around at that time was significant, would have been higher than their risk of getting cancer in any case. I mean, we're all going to die of something, and on average, 20 to 30% of us are going to die of cancer. So you're not going to, on an individual risk basis, don't go home and think I was, as an individual, was overexposed from this accident. But there's a different assessment of whether, when you expose a large population to a very small radioactive insult individually, the sum of those individual risks can get up high enough so you can get some cancers in the population. You'll never be able to sort them out from the background risks, but you could make a claim that there were cancers induced in the population from this accident, while the individual risk you wouldn't particularly worry about. But these are arm-waving arguments. I mean, there's no quantitative data to I mean, I have not done any calculations, and so I won't go beyond that. That sort of summarizes my take on this, and be happy to debate my colleagues and anybody else in the room. I do wish I had the DNA of those of you who were working at that plant and are still here to discuss this today.
Thank you, Dr. Cochran.